Introduce Umberto Hryniewicz from Aachen, is how it's pronounced, University. He's going to speak on systolic inequalities in symplectic topology.
Thank you. Good morning. First of all, I'd like to thank the organizers for the invitation to speak. It's a pleasure to participate. And I'd like to first introduce some notation, recall some basic definitions. I will always consider R2n with its standard symplectic structure. So viewed as, so this is the same as viewing R2n as the cotangent bundle of Rn. So this talk is about studying estimates on symplectic capacities in terms of volume and other quantities of interest. And so let me recall what is a symplectic capacity. Symplectic capacity is a function on the set of symplectic manifolds of a given dimension to the non-negative real numbers are infinity and satisfying a few axioms. Most important one is the monotonicity property. So if one manifold symplectically embeds into the other, then the capacity cannot get smaller. The second property is called conformality property. If I scale the symplectic form, the symplectic capacity gets scaled by the same factor. And the third property is a normalization condition. Asserting that the ball and the cylinder have capacity equal to pi. So here the ball is just the unit ball in these coordinates, unit Euclidean ball, and the cylinder is the symplectic product of a ball of radius r in dimension 2 across 2n minus 2 dimensional symplectic vector space. So this is this ball, and this is where the other coordinates live. Okay. So the main motivation for for the results I'm going to present is so-called symplectic isoperimetric inequality, or Viterbo's conjecture. So let me first define the objects of the. So I already defined capacity. I need to define what is a convex body. So a convex body on a vector space over the reals is a compact convex set with non-empty integer. Okay. So the symplectic isoperimetric inequality or isoperimetric conjecture also known as Viterbo's conjecture, because around the 2000s, asserts that, or asks for certain inequality to hold, which is this one. The ratio between capacity to scale to the appropriate power evaluated on a convex body is not larger than what you get for the unit ball, where here is C is any convex body in R2n. And the volume is the volume computed. So volumes are computed with the volume form induced by the symplectic form. Okay? So in some sense, well, that's what it is. And before going on, let me state an even wilder conjecture. So this conjecture was made by Viterbo in a paper published in 2000. This wild conjecture, I don't know who's this dude, and I don't know which year. All I know is that at some point in year 2005, at least one person believed in this conjecture. That's all I can say about this conjecture. And I can tell you this because I was told to study this conjecture during my PhD, and I did some constructions, but I mean, I fell short from solving it. Luckily for me, I could take what I did and then apply the analysis that I studied to other problems. But the conjecture states that so for every convex body in R2n and for every pair of symplectic capacities, the following holds. So uniqueness of capacities for convex bodies in R2n. Nowadays, I'm not sure if the set of people who believe in this conjecture is non-empty, or I think it's probably empty, I don't know. But I will just note that this conjecture implies Viterbo's conjecture. Just because, well, if every capacity is equal, then I mean, any symplectic capacity gives the same value on a convex body in R2n. Okay. So Viterbo's conjecture follows from this just because, well, the Gromov width is obviously less or equal than the square root of the volume. So this means that wild conjecture implies Viterbo's. Okay. I just want to finish this discussion about conjectures by mentioning the Malheur conjecture. It states that, well, let me just say that if you have a convex body in Rn, convex body, centrally symmetric, this means that k is equal to minus k. So you can think of it as the unit ball of some norm, and you can define the dual ball and then the Malheur conjecture asks for the product. And now by this I mean product volumes, but Euclidean volumes, to be at least equal to 4n times n factorial. And this number is just the product volume. So this is called the product volume or the Malheur volume. This number is the product volume of the unit L1 ball. Okay. And this conjecture, so one way of interpreting what this conjecture means is that this is some kind of measure of how round this convex body is, and this is saying that the less round body is this one. So this should be complemented by a result Blaschke-Santa law, which is this is always equal, less or equal than, well, the product volume of the unit ball. So the unit Euclidean ball is the roundest centrally symmetric convex body, and this is expected to be the less round. And there's a very nice result of Artestein Avdan, Karashev, and Ostrover, which basically states that the Viterbo's conjecture implies the Malheur conjecture, which is, this follows from the following inequality. If you compute the Hofer-Zehnder capacity of k times k polar is equal to 4. Okay. So since the Euclidean volume, since this thing would be 1 over n squared, n factorial of the symplectic volume, this is just, by Viterbo, this would be implying that this holds. Here there is a relation to billiards. It's a very nice paper. Okay. That's the relation. For every centrally symmetric convex body, this equality holds. So this, right? I mean, if you Viterbo for the Hofer-Zehnder capacity would imply this inequality here. It's the same. Okay. Okay. So before I move on, let me make some remarks on definitions. The first one is, so I'm going to consider So for giving a smooth compact domain in R2n, I'm going to define the systolic ratio of this domain to be equal to minimal action of gamma, where gamma is a closed characteristic. To the n divided by the volume. So closed characteristic just means that gamma dot is contained in T in the symplectic orthogonal of the tangent space of the boundary at every point. So it's, if you see the boundary as a regular value of a Hamiltonian system, this would be a closed periodic orbit of this Hamiltonian system. That's the systolic ratio. And so balls have systolic ratio equal to 1, as you can check. So B, I'm going to call such a domain Zol if every characteristic line in the boundary is closed, and they all have the same action. So like, for instance, the boundary of the unit ball would be such an example, but the boundary of a rational ellipsoid would not be such example unless it's the ball. Okay. Let me state one little lemma which is going to be useful for us. So it's not hard, but also not too easy to show that if in 4 dimensions a domain is all, then there exists a symplectomorphism such that the image of omega by the symplectomorphism is equal to the ball of radius r, where r is given by asking that pi r squared is the action of the closed characteristics on the boundary. Okay, so basically there is, up to symplectomorphism, there is only one Zoll domain dimension 4. So final remark I would like to make is that if omega is convex, again assuming it's smooth and compact, then there are symplectic capacities C such that the C of omega is equal to the minimum, so it's the minimal action of closed characteristics on the boundary. So there is at least one. In the book of Hofer-Zender, it's claimed that Hofer-Zender capacity works, but also there is a recent preprint by Abondando and Kang stating that this also works for another capacity which is built from symplectic homology.
You say complexity means strict complexity?
Yes. Oh, let's say that just to make sure. So this means that the boundary, well, the curvatures in the boundary are really positive. Okay. So the first result I'd like to state is joint work with, so A is equal abundando, B is equal Barney Bramham, and S is equal Pedro Salomão. It's stating that if omega in R4 is C3 close to Zol, right? So I'm saying that something is going to hold for every omega which is in the C3 neighborhood of some Zol domain. Or more precisely, given a Zol domain, there is a C3 neighborhood of it such that something is going to hold for every domain there. Then C3 close to Zol and star-shaped. So star-shaped really means that, well, this domain, there is a point in the interior such that if I start issuing rays from this interior point, then every ray meets the boundary transversely. So if you have a star-shaped domain C3 close to a Zol 1, we have this inequality. Equality holds if and only if the domain is all. So this is basically saying that for domains close, so near the ball, Viterbo's conjecture holds for any capacity that picks up the minimal action. Okay. There is also a paper by EDA. Okay. Okay. Thanks. Okay. So let me. It's going to. So it's going to preserve all. I mean, you can make the region where you don't know if it preserves or not very small. If it could be a neighborhood of a point.
Because if it preserves the UFE form, then if it's solved, then it's star-shaped.
Yeah, but we don't know if it does. Not everywhere, at least.
It's not clear if it's solved and then it's star-shaped.
If it's not clear if it's
Solved, it's star-shaped.
No, I mean we don't ask. Sorry, star-shaped. Yes. So I did an assumption here. Star-shaped ends all, then there is such a guy. Because this is built like this. I mean, first of all, there is a strict contactomorphism from the boundary to the boundary of this ball, and then you extend this strict contactomorphism to, in a one homogeneous way, to a homeomorphism of R4, which is going to be smooth except for a point in the interior. and then you modify there to make it smooth and still keep it symplectic. So it certainly uses star-shaped form of this domain. Yes?
Sorry, are you saying star-shaped is necessary? It's necessary for the proof, but it's necessary for the state?
I'm saying that star-shaped is a part of the assumptions. So if it's a Zoll domain, which is star-shaped, then this holds. That's what I'm saying. It's part of the assumption.
And you do need your theorem, is it true without star-shaped?
Yeah, just because I don't want to say that this guy from which you want to perturb is star-shaped. If it's a ball, then this would follow. But since for this lemma I need star-shapedness, you don't know if you start from a Zoll thing, is it necessarily a ball or not? So we don't know.
So in this result, you don't need that the Zoll guy is star-shaped.
No. Okay. So actually, yes, we need. Sorry, we need. We need to assume it's Zoll.
Since the guy is Zoll, then the guy Citricos, since the Zoll guy is star-shaped, then the Citricos guy is also star-shaped.
Yeah, so let me say it like this. So if it's C3 close to a star-shaped zone, then yeah, that's right. Okay. So let me describe one application which is called middle dimensional non-squeezing. So let me recall Gromov's non-squeezing. So it asserts that if a certain ball of radius r symplectically embeds into a certain cylinder of radius r, then, if and only if, but the hard part is this direction, then this inequality holds. So there is an equivalent way of stating this in terms of projections. So this is equivalent. So Gromov's non-squeezing is equivalent to asking the following. If you have a symplectic embedding of the unit ball into R2n, and V is a two-dimensional symplectic linear subspace, then the volume, but this will be just area, of the symplectic projector applied to the image of this ball is at least equal to pi. So the symplectic projector is just the projection, right? So here you have V, and then you have the symplectic orthogonal. So this is just a projection to V along the symplectic orthogonal. So this is equivalent to Gromov's non-squeezing. So this formulation motivates generalization to higher dimensions. So middle dimensional non-squeezing would ask for the following to hold. So the volume of a symplectic projector applied to the image of the unit ball by symplectic embedding to be at least equal to pi to the kth power, where the dimension of symplectic subspace is equal to 2k. And that should hold for every V and for every symplectic embedding. So then one should ask, then, is this true or not for every symplectic embedding and for every V? And the answer is, so let's say, does this inequality hold for every V and phi and phi? And the answer is studied by, so it's given by Abondandolo, so Abondandolo and Matveyev. So the answer is no in general, but yes if phi is linear, is symplectic linear. So one should ask then, is this purely a linear phenomenon, or does it extend to the nonlinear symplectic embeddings? And basically, we're going to apply that result to show that this is actually true if phi is close to linear, and then this has certain implications. But first, let me just say that Viterbo's conjecture implies mirror-dimensional squeezing. And probably, well, let's see that. So suppose you have a ball and you have a symplectic embedding. Here's the image of the ball. Have the symplectic projector. Here's V. And here's the image, the shadow of this guy. Then we want to show that the volume of this thing here is at least equal to pi to the k, where 2k is the dimension of this thing. And so first ingredient is a lemma due to Abondandolo and Pietro Maia, stating that if you have any symplectic capacity which picks the minimal action of a closed characteristic on the boundary, then this is at least equal to so the symplectic capacity of the projection is at least equal to the symplectic capacity of the unprojected guy. That follows from it's kind of easy if you know some some hard definitions. So it follows basically from an analysis of the Clark dual functional and the fact that the minimal action is also the minimum, the minimal, absolute minimum of the Clark dual functional. So, but if you have this ingredient, then you can do the following. You can take the volume of the projected guy. So by Viterbo, sorry, I forgot to say one very important assumption here. Viterbo's conjecture implies mirror-dimensional squeezing if the image is convex. Otherwise, it's going to be. So let me draw a convex image here. All right. Okay. So by Viterbo's conjecture, we would have, so this would be convex as well, so we would have C of this guy to the kth power, so this is Viterbo. Then we would apply this inequality, we would get this inequality, and this is equal just to pi to the k, just because symplectic capacities are preserved by symplectic. Yes. Okay. So a corollary of our result implies that, so mu-dimensional, non-squeezing in dimension 4. So I'm assuming that the dimension of V is 4. This is implied by, so this is, okay, so in dimension 4 holds if the symplectic embedding is C3 close to linear. That's a corollary. And the proof is just, so the proof doesn't quite follow from this argument because we need another ingredient. So we need a lemma also by Abondando and Matveyev, asserting that in general, let's say M is a symplectic linear map. So the volume is always at least equal to pi to the k with equality if and only if this thing is symplectomorphic to the 2k unit ball, so symplectic. So that's a lemma on symplectic linear algebra. Okay, so with this lemma, we can then follow the same argument here, basically. So you want to show, so now this guy would be C3 close to linear. We want to show this is at least equal to pi square. Recall that the dimension of V is 4. Okay, so, all right. If phi is close to linear, by that lemma, this would be close to Zoll. So you could replace Viterbo by the perturbative Viterbo, get this inequality, and then the other one follows just as here. Okay. So. Consequence is that you can, so basically, this corollary implies that locally every symplectic embedding satisfies 4-dimensional, so middle dimensional squeeze dimension 4. It's because locally a map is approximated by its derivative, which is linear. Then, okay. So whatever symplectic embedding you're talking about, locally, you have such an inequality. Okay. So the reason why I think it's an interesting question, this middle dimensional squeeze, is because it's false in general, but it holds on a neighborhood on an open set of symplectic embeddings. So the question is, what is the threshold? I mean, when does middle-dimensional symplectic, so middle-dimensional squeezing fails? It holds close to linear, fails in general. What is a property of a symplectic embedding the boundary of this, between yes and no? This is a typical question in geometry, in systolic geometry. Usually, you have certain systolic inequalities which don't hold in general, but hold in certain cases. And it's always a fascinating question in systolic geometry to understand what is the threshold, what is the sharp systolic inequality. So this would be a question about sharp systolic symplectic embeddings. Okay, so that's what I wanted to say about middle dimensional no squeezing. Now I want to go in the last 13 minutes, or 18 minutes, 17. I want to discuss a bit about the wider conjecture, about the conjecture about uniqueness of symplectic capacities on convex bodies. I don't know if I believe, actually. I mean, I don't have a good reason to believe it. Also don't have a good reason to disbelieve it. What I'm going to try to tell now is why at some point I had a good reason to disbelieve it, but then I changed my mind. So basically that's... Sorry? Well, should ask Helmut about that. The precise answer to this question is probably known to Helmut.
Why don't you try to do, instead of the minimum action, the maximum action? Why would you do that?
Well, the maximal action could be infinity. I mean, if you're talking, if you consider iterated orbits, so in general it's infinity.
Because you divide by the volume, so I could not find a way of...
It's
Generically infinity, because you have long... Yes.
Oh, I see. You just perturb a little.
Yeah.
So that you have a very long...
Yes.
I see. But couldn't you ask for the maximum closed one?
Yes, the maximal action among a closed characteristic in general is infinity. Okay. So let me tell you a crazy definition by Hofer, Vysotsky, and Zander, then let me explain why is it a relevant definition. So H is Hofer, I'm going to give it the definition relevant to our context here. So a domain, again, is smooth convex, smooth compact, is dynamically convex. Let me just simplify it very, very much just to fit the context I want to talk about. If it is star-shaped and this inequality holds for the Conius-Linder index for all closed characteristics. So realize the boundary of the domain as a regular level of some Hamiltonian. Then you have Conley-Isner index of periodic orbits. That's the Conley-Isner index I'm talking about. Okay. So HWZ proved that this is true if the boundary is strictly convex. And they proved a very deep theorem in dimension 4 that if the domain is dynamically convex, then the boundary carries a disk-like global surface of section for the characteristic flow, say, for any flow which is tangent to the characteristic lines. So this thing is just an embedded disk whose boundary is a periodic orbit, and at every point you can trace back and forward the characteristic line to that point to hit the interior of this disk transversely. So basically you can encode the dynamics on the return map to this disk. So they asked in the same paper, so can we pick gamma meaning the boundary of the disk-like global surface of section of minimal action. And, well, then as a corollary of the results of my thesis, I show that gamma bounds a disk-like global surface of section. So I'm going to abbreviate global surface of section by GSS. In dimension 4 again, of course. If and only if gamma is unknotted and the self-linking number of gamma is -1. So then this question translates to the following question. Is the minimal action among closed characteristics equal to the action of an orbit which is unknotted self-linking -1? Well, in view of the fact that the minimal action is a capacity, you could then try to show that gamma, so the minimal action among orbits which are unknotted self-linking -1, if you can show that this is not a capacity, then we would not only answer this conjecture, but also disprove the wild conjecture about uniqueness of capacities. So then, let me define, let's say, C Hopf of omega dynamically convex to be the minimal action of a closed characteristic on which is unknotted self-linking -1. So then, well, okay, so it would be great if we could prove this is not a capacity, but fortunately or unfortunately, this is a capacity. Actually, you can even generalize, so we can do a standard trick, what Vinicius mentioned. You can say this is a sup of C Hopf omega So Vinicius mentioned this trick on school, symplectic topology last week. And the theorem one can prove is that C hop is a capacity. Which if it was not a capacity, we would have answered this question. But it is a capacity, which is maybe a good thing or a bad thing because we don't know if this is equal to the minimal action or not. Right? So the question is, so this question then becomes, is this capacity equal to the minimal action, equal to say the Hofer-Zeller capacity or symplectic homology capacity or not? So I think it's a very interesting question. And there is another question in this field. So I mentioned that Hofer, Vysotsky, and Zander proved that dynamical convexity in dimension 4 imply, so it's not this statement. So they proved that strict convexity of the boundary implies dynamical convexity in dimension 4, actually in any dimension. But the question is the converse true? Given a dynamically convex, so given a domain with dynamically convex boundary, is it true that it's symplectomorphic to another domain with strictly convex boundary? And Leonardo is going to mention some results in this direction, very nice results using symmetry. So it's not the proof, but it's a very nice statement. But the question is this true? And, well, there is a result, again, collaboration with Barney, Pedro, and Alberto, saying that, well, there exists dynamically convex domains such that the systolic ratio is close to 2. So which implies that Viterbo does not hold for. So Viterbo didn't conjecture anything about dynamically convex. I'm saying that the version of Viterbo's conjecture does not hold for dynamically convex domains. So if Viterbo holds, then we answer this question, which is also a nice implication, this set of ideas. Okay. I just want to finish by, I have until 11:15, right? Is this right? So I basically, in this talk, I just wanted to tell you about a bunch of open questions which are related to important conjectures inside symplectic geometry and also outside of symplectic geometry, like the Malheur conjecture. And they're all somehow interconnected. You have some like tentacles of this set of questions going to dynamics, some other tentacle of this set of ideas going to geometry, Riemannian geometry. So, and they're all interconnected by a common intersection in the realm of symplectic geometry. So I think it's an interesting discussion. So then, I've been for some years talking about this number C hop with Michael Hutchins and Vinicius Ramos, and seems that they have an argument to prove that C hop is equal to C1 ECH. So let's say, let me put this in progress, I guess, or in discussion. So this, to me, is a nice inequality because, first of all, this is like a number which comes from abstract nonsense from a certain homology theory. So it's nice to explain it in terms of a more concrete geometric assumption. And this is a number which comes from very specific geometric construction, which then is also nice to explain this guy as a spectral invariant. So I think it's a good interplay between. So this number, this formulation explains this one, and this one explains that one. So I think it's. So the question is. So that's for omega. Dynamically convex. So it would be nice if this insight here, so this information, it would be nice if it helps showing that this is the minimal action somehow, or not. If it doesn't help, bad, but if it does, it would be great. If this number would be the minimal action, then we would answer this question. And if not, we disprove uniqueness of capacities. Okay. All right, I think I'll stop here. Thank you.